Hello. So this is Monday, October 5th, and this is ECE641, model-based imaging. And today we're going to pick up on Chapter 7, which we started. So Chapter 7 is all about map estimation with non-Gaussian priors, okay? Or non-quadratic regularization is the other way to see it, okay? And so the problem is that how do you do this optimization problem when one of the terms is not quadratic, basically, is what it comes down to. Okay, are there any questions? Oh, somebody asked about the exam. So the exam is scheduled for next Friday, I guess. There'll be more on that later. We'll see how that goes. But the, oh God. Okay. So the thing is like this. Okay, so do you want to compute a map estimate, okay? And it's the arg min, okay, over x of something like 1/2, say y minus ax squared. And maybe there's a weighting matrix here. So this is the interpretation as being the inverse covariance of the noise. What do you call the inverse covariance? It's also what has a different name.
The precision.
The precision matrix of the noise, right? So the precision matrix of the noise tells you the conditional distribution of y given x, right? Because if you know x, then the expected value of y should just be ax, right? And then this difference is then going to be distributed as the noise, right? So then this is the conditional precision matrix for the noise, okay? And then plus something else over here, which is u of x, okay? Now, in the previous sections, this was quadratic. When things are quadratic, it's easier to compute minima, okay? First of all, you can write a closed form solution in the quadratic case in terms of matrix inverses, right? But the problem is you really can't compute the matrix inverse for these problems. Why? Because those matrices are huge, okay? Huge, okay? So this matrix, like, so y equals ax, I write a, but I almost never really try to store a directly. The only times you would maybe store a is because a is almost always very sparse, okay? Because otherwise, how could you have that many parameters? You wouldn't know how to set them, okay? Because there's like, if this is 1,000,000 pixels and this is 1,000,000 values, then this is 1,000,000 squared. It's too big. I mean, what are you supposed to do with something that big, right? Even when this is dense, there can be cases where it's dense, okay? But even when it's dense, it's not really dense because, like, an example would be you might have y equals f of x, where this is the DFT. The discrete Fourier transform is a dense matrix, right? But you don't really use it that way, okay? Because the discrete Fourier transform can be written as a series of sparse transformations. And when you do that, what do they call that? Huh?
Yeah.
They call it the FFT, right? Because when you draw a flow diagram, I don't know, we haven't talked about FFTs, but I'm assuming most of you have been exposed one way or another to the concept of an FFT. You have these butterflies, right? Like that. Does that sound familiar? That's how you compute an FFT, right? If it's a power of 2. You have what they call butterflies, okay? That represents 4 multiplies, 4 complex multiplies. And then you do butterfly this way. Like this, okay, something like that, right? So this is a sparse transform, this is a sparse transform, but the composition of the two sparse transforms is dense. So how many multiplies does an FFT really take? Does anybody know? If you have an endpoint FFT, how many multiplies does it take, roughly?
It's like n over 2 log n.
It's the base, it's the log base 2 of n. And the reason is each layer of FFT takes like 2n. It takes 2n multiplies, complex multiplies. And how many layers are there? Well, there's log base 2 layers. If it's a 4-point DFT, there's 2 layers. If it's an 8-point, there's 3. It's 16. So this is the number of multiplies. So it's really it's a composition of sparse transformations. In reality, for real images, you never have a truly dense transform, because if you had a dense transform, like, how are you going to do that, okay? I mean, never is a strong word. I mean, I'm sure that you could come up with some case where somebody did it, but even then, they'd approximate it by something sparse, okay? So my point is that these matrices, they're beautiful conceptual mathematical ideas, but you don't really use them directly, literally, okay? There used to be this concept I'd heard about, a thing called omega, okay? And it's the number that encodes all the information about the state of the universe, okay? So it gives you the position of every quark, like, in the universe. So from this, I can figure out what you're thinking, you know? I can calculate the trajectory of muons from Venus, okay? And it's only one number. It's a beautiful thing. So you know, it's like, oh, all we need to know is that one number and we're good. Of course, getting that one number is a little tricky. So the reason I'm pointing this out is that this is the power of the abstraction of mathematics, right? You can encode monstrously complex, literally, well, I'm not sure exactly what it means to be literal in this case, but I'll use the word anyway. Literally mind-boggling, because it literally boggles my mind, okay, to think about such a thing, okay? It's literally I would argue it's literally. I don't use, like, I hate it when people use the word literally. Like, I was literally flying on wings. No, like, you weren't literally flying on wings. Like, it's not literal, okay? But here I would say it's literally mind-boggling, because my mind is actually boggled. Maybe yours isn't, but mine is, okay? So it's literally mind-boggling. It's very powerful. That's what's beautiful about mathematics. You can express very powerful ideas in very simple ways, okay? But of course, the price you pay for that is you sweep an enormous amount under the rug, okay? But same thing here, this A thing, you don't literally use it. It's a concept, right? It's conceptual. Usually what ends up happening is that, okay, like with the FFT, you don't know, if you're doing 1024 FFTs, you don't literally calculate that transform matrix. You have a program, when you want to multiply A, when you want to multiply F times X, what you really do is you call a program called FFT, and give it an input of x, okay? So you don't literally do a vector matrix multiply. You just calculate what the answer would be if you did do that literally, okay? So this is a powerful concept, but you have to be careful, right? Now, so the A matrix, you don't really want to store in MATLAB. I mean, that's the first thing that person does, and it's good that they do that. If you did that, don't feel bad, okay? Because one needs to do that once in their lives to realize that it's a bad idea. Okay, you're like you have this like big image, and you're like trying to store the matrix in MATLAB, and you're like, this isn't working. MATLAB's running out of memory. Okay, and you go, what's the problem with MATLAB? Well, the problem isn't really with MATLAB. The problem is you're trying to do something that doesn't make sense. Okay, it's like you're trying to dig a hole to China with a toothpick. Okay, like it doesn't make any sense, right? So it's not physically a reasonable thing to do. So, yeah. So now to compute the X map hat, if you had if this thing was quadratic, you'd have X transpose BX, and maybe this would be 1/2. Okay. Let's say it doesn't have to be. Do you have a question?
No.
Oh, okay. Okay. If anybody has a question, please ask. Like, you know, don't hesitate. It's a small class, so it can be like, you know, don't. Then you're going to have A transpose lambda A plus B inverse times, then this is A transpose lambda Y, okay? So you can write it down in closed form in that case, but the problem is that this matrix here is huge. And worse that, you have to take its inverse. So you're not going to do that. So instead what you do is you say, okay, but I'd be better off just directly solving the optimization problem. So now if it's quadratic, okay, fine. Now if it's not, now if it's quadratic, oh, maybe I should have left that up there a little longer. If it's quadratic, solving this optimization problem, even if you're going to do it through numerical optimization, is easier, okay? Okay, why? Because, well, let's say you're going to use gradient descent. All the methods of optimization basically boil down to 2 steps, or not all, but most. First, you compute a direction, then you do a minimization along that direction. The second thing is called a line search, okay? Now, if this is a quadratic function, that means, so this whole thing here we're going to call f of x, right? Right. So then you have f of x plus alpha d. So x is your current point, d is the direction you're going in, and alpha is like the knob you're turning to control how far you go, right? So the picture is like this. So the picture is like this. You have a point here, that's x. This is d, right? And alpha is the distance you travel along there. Now, presumably, you pick the distance so that you're trying to solve minimization. So if the inner product of d with the gradient is positive, then you're going in the wrong direction because you're going uphill. So you want d to be in the direction of the negative gradient. So you want an inner product with the gradient to be negative, less than 0, right? Otherwise, you're going in the wrong direction. Seems like a bad idea, okay? Now, one could argue whether it's best to go exactly in the opposite direction of the gradient. There could be other directions that are better, but you definitely don't want to go into a direction where you're making the function bigger. There's really no advantage to that, right? So when you go to do this plot, this is alpha, right? When alpha is 0, the output's going to be whatever it was at f of x. Now, the slope has to be negative here, because I told you I'm not going to accept these that have a positive inner product with the gradient, because that would be silly. Don't take that value, okay? So you're going to make sure that the gradient's negative there. So that means you have to start off going down, right? Now, this is a convex function. Actually, we're only going to consider the convex case, even if it's not quadratic. But it's going to be a convex function, so it's going to look like this. Furthermore, this is a quadratic function, so if I take this, it's got to be a quadratic function of alpha, right? Got to be a quadratic function of alpha. So that means this thing is, if you have a quadratic function, it's parameterized by 3 values. Right? Quadratic, it's like a Taylor series. There's more than one way of parameterizing by 3 values. You can parameterize it by the first, second derivatives and the offset, okay? So that would be like, you can make it 1/2, I'll call it theta, 2, oh gosh, what do I use then? I guess I use it theta 2 times alpha squared plus theta 1 times alpha plus c. That's the first 2 derivatives, because this is the Taylor series expansion, so that's the second derivative, right? So it's got to have this form, correct? If it has that form, I can solve for the minimum, right? So I'll call this thing g of alpha. Ignore the fact that there's this other function here. I call it g of alpha. So I have that. Everybody knows how to find the minimum. You compute this thing and you set it to 0, right? So let's differentiate. We get theta 2 times alpha plus theta 1 plus 0 equals 0, because the derivative of c is 0, right? So we get here that alpha equals minus theta 1 over theta 2. You know, the most beautiful things in life are very simple, you know? Like bamboo umbrellas in Mai Tais, okay? They're very simple things that are fun, okay? And this is a very simple thing that's fun, okay? What the heck does it mean? It means that if you want to find this minimum, okay? This is the derivative, see? That's the minimum. I'll call it alpha star. You're solving for the root of the derivative, right? So, yeah. Okay, so you're at this point here, okay? And the second derivative is the curvature, okay? So the second derivative is the slope of this thing. Here the slope is positive, okay? And the value, this is theta 1, which is negative, by the way, right? And the slope is equal to theta 2, okay? So if you want to find this point of intersection, you take the negative of theta 1 and you divide it by theta 2. Because theta 2 is like the velocity, I guess. Does that make sense? I mean, you could just do the geometry here. It's like really simple geometry, right? If this slope is theta 2, if theta 2 gets larger, then you'll hit faster. Okay? So you got to divide by theta 2. And there's got to be a minus 1 here, okay? Because obviously you go forward if this is the thing over here, right? Because this is a negative number. Theta 1's negative. Does this make sense?
What theta 1, I guess I don't see why theta 1 needs to be negative necessarily, because you might not cross the 0 axis.
Well, but you have to take the negative. Yeah, okay, theta 1 here, over here is negative, right? You agree with that, right?
No, I guess, what if you don't have a 0? What if your quadratic doesn't cross 0? So your f, or your g of...
Yeah. No, I get that. Okay, hold your thought for just a moment.
Okay.
I'm not disagreeing with you. I'm not invalidating your statement, okay? I'm just saying, on this picture right here that I drew here, theta 1's negative, right?
Sure. Yeah.
Okay, so you agree with that, right?
Yeah.
And then, so I have to take, so this will be like negative 2, so I'll have to take minus negative 2, which will be 2, And I'll divide that by the positive slope to get theta star, which is positive, right?
Sure.
Now, what you're saying is, what if that calls up here? Well, then the answer is that there's no, well, okay, there actually is, that, okay, it'll be like this, right? Then it won't cross.
Right.
The solution, that's the case where it goes like this. Or actually, it's not even like that. I'm sorry. It's like this, okay?
Would it not be the case such that it just doesn't cross? Because doesn't it only cross at 0 if the...
But I started off by saying, what you're saying is correct.
Oh.
Okay, I started off by saying I'm going to take a D to be in a direction so that the inner product with the gradient is negative.
Okay.
So if the inner product with the gradient, here in the case you described, the inner product with the gradient has to be positive. Right? But it's a perfectly valid case. Actually, in a more general framework, it would work. All this. What would end up happening is if there was a solution, the slope would have had to been negative. You know, you can work through it out. My point is that, you know what it is? This is a little bit like, you know when you're writing for loops and you're like, I don't know whether I should, is it I plus 1 or I minus, or do I use I? Okay, so you always do it for like the case 0. Because you know if it's right for the case 0, it's got to be right for the other cases. That's what I'm doing here, because I'm like saying, okay, let's do it for one special case. It works out. It's got to be right for the other cases.
Okay, sure. So theta 1 has to be negative if your direction D has a negative dot product or product with the value f of x.
Yes. So D transpose gradient of f of x has got to be less than 0. Because we're doing minimization.
Right.
Now, it could be I picked a D such this was not true, but that would be a really bad thing to do, so let's just not do that.
Okay, that's all. Thank you.
Right? Okay. As I said, it's the simple things in life that are important. So I'd like to really, the questions you're asking are beautiful because you guys can go through all the complicated equations. I just want you to get the basic idea, the really core, essential idea, right? Then you plug all the things in, you get some big, messy equation. But the central concept is still the same, okay? This is called Newton's method. Newton-Raphson's. Have people heard of Newton-Raphson algorithm for rooting things? This is just Newton-Raphson, okay? But the difference is that because the function's quadratic, its derivative is linear, Newton-Raphson is exact. It gives you the exact solution in one step. You're done. Okay? Okay, now, the problem is, so everybody's good with this. Now the problem is we want to go to the case where it's not quadratic anymore. Okay? It's not quadratic anymore. So u of x is not quadratic. So now the problem is that you can't compute a closed form update for alpha. So whenever, the other thing here is that, so theta 1, by the way, is equal to the derivative of f of x plus alpha d alpha, okay? And I can compute what that is, okay? In terms of the gradient, it's going to turn out to be, the gradient, it's actually going to turn out to be equal to d transpose times the gradient of x. Oh, at alpha equals 0. Which is precisely the thing I said has to be negative. Okay, so theta 1 is going to have to be negative. And I could go through the same argument for the second derivative. Okay, in the case of the second derivative, it gets a little more complicated, but let's not worry about it. Okay. Actually, it was worked out in chapter 5. It gave you the closed form updates it gave you the closed form solution for how you compute the exact value of alpha that gave you the optimal greedy, which sounds contradictory, update. So in other words, it found the value alpha star, which minimized this function. Now, I don't want to get off onto a tangent, but remember, there's 2 steps. You pick a direction, you minimize. It's not actually necessarily the case that the very best thing to do is to minimize. It's very best in the sense that it gives you the minimum value of the cost function for the step, but it might actually turn out that you have a sequence of steps, right? And for whatever reason, it might actually be better not to do the minimum. Maybe it'd be better to go shoot past the minimum a little bit, or undershoot the minimum. And there's things called successive under-relaxation and successive over-relaxation. And they give you, they can actually have better convergence. So the point here is that this is an optimal solution to a greedy update. So it's optimal in the sense that it optimizes this greedy update, but it doesn't necessarily produce a global optimal algorithm. So the way to think about it here is that you have a bunch of companies, right? And then each company might set the parameters of their company, the pricing for their company, to produce an optimal outcome for that company, right? But it doesn't necessarily mean that that's going to produce an optimal outcome for the economy. It could be that they could all get together and do something suboptimal individually that would be globally optimal for the group, right? Everybody understands that idea? So, but nonetheless, we start here. This is a reasonable place to start. And this would be the optimal update for the greedy update, okay? Okay, now the problem is, let's say it's not quadratic. If it's not quadratic, right? So now what are you going to do? Well, the idea of Newton-Raphson still applies. So you could still do Newton-Raphson updates, okay? So you could put Newton-Raphson. Raphson. Is that how you spell Raphson? Okay, well what happens is that you have f of x, okay, is equal to all that stuff, okay? Is equal to whatever it was before. It's 1/2 y minus ax squared, just lambda here, plus some u of x, all right? Now what you do is you compute theta 1 is equal to d transpose, because you've computed d somehow or another, okay? I'm not raising the issue, how do you compute d, because that's another question. That basically selects between different types of algorithms. But once you pick a d, you always have to do a line search. So if you're doing gradient descent, d will be the negative gradient. If you're doing conjugate gradient, there's some kind of more complicated thing you do, okay? If you're doing preconditioned gradient descent, which we don't really talk about very much, but is pretty commonly used, you take the gradient, you multiply it by some positive definite matrix. Preconditioned gradient descent is basically what all those algorithms in deep learning use. Because they compute a gradient with back projection, and then they do some kind of scaling of the components. If you do scaling of the components, as long as you're scaling by positive numbers, that's a positive definite matrix, because it's a diagonal matrix, and a diagonal matrix is positive definite if its elements are positive definite. Why is it a diagonal matrix? Because I'm taking each component of the parameters and I'm multiplying the scaling them by some factor, so that's effectively a diagonal operator. I don't know if that made any sense. But the big point is just this. Preconditioned gradient descent represents all optimization algorithms used in deep learning. Okay? It's just the different preconditioners and stuff. So then you multiply this by the gradient of that. And that's why you have to compute the gradient in deep learning. And the gradient you compute using back projection. Okay? Not back projection, back propagation. Back propagation. And then theta 2, oh God. What is theta 2? You have to compute the second derivative. Blah, 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 blah. I don't know. I'm not going to worry about it. Okay. The details of, in principle, it's not that hard. You have to compute the Hessian is the problem, and then the Hessian is another one of these matrices that's god awful horrible that you never compute. So you don't really compute the Hessian. So let me skip that. Okay. The other possibility, if you do, is right. Okay. Anyway. Okay, oh, by the way, you could also evaluate the gradient at 2 points, okay, and then you could get the second derivative that way. Okay, fine, whatever. And then you have alpha equals minus theta 1 over, oh, this is theta, yeah, over theta 2. Okay, now, and then what happens is like this. Now what happens is you have a non-quadratic function, so it's something a little more complicated, I don't know. It's convex though, let's say. So what ends up happening is the derivative looks like this. It might look like that. The derivative's monotone increasing. If the derivative is monotone increasing, it means that the function must be convex. Why? Because, okay, if the function is a sufficient condition for convexity is that the second derivative be strictly positive, right? Everybody knows that. So if the second derivative is the derivative of the derivative, right? So the derivative of the first derivative is the second derivative, right? So my point is this, the slope of this derivative is the second derivative. So if the slope is positive, then it has to be convex, right? Well, if the thing's monotone increasing and it's continuous, it's got to be positive. It has to have a positive slope, right? So this is this has got to be a convex function in that case. And here, as you can see intuitively, why convexity is so important. Because if I know that I have some value here, right? I start off with a value which is negative, which means to say that the slope is, the gradient's negative. And of course the gradient's negative because you wouldn't pick a direction where the gradient was positive. So if you, okay, so it's going to go down. And then, well, then I know I've got to only have a single crossing. Because if it came down again, well, that would violate my assumption that the thing had it was monotone increasing. So convex functions will have a unique solution. Now, I'm lying a little bit because this could have a flat region, okay? In which case this would be flat, okay? So the solution wouldn't be unique. But as long as I say this is strictly convex, then I'm saying the second derivative is strictly positive. Then this function has to be monotone strictly increasing. Then I can only have a unique solution, okay? So that's the intuition behind why convexity is so important. So now what will happen is if I use the Newton-Raphson algorithm, this is theta 1, right? And then the slope here, that's theta 2, correct? So this will be the solution. I'll call this theta, say 1. Because it's no longer theta star. This is theta 1. And then I could, so that gets me closer to the solution, right? Then I could repeat it. And that's called the Newton-Raphson algorithm. Are people familiar with the Newton-Raphson algorithms from some other experiences? Okay. The problem with the Newton-Raphson algorithm is it isn't necessarily convergent. In fact, it can diverge. It seems like a pretty reasonable thing to do, but it doesn't always work. Okay. Why? I don't want to get off into too much of a tangent, but basically you could see how you could have kind of bad things happen. Let's, is it right if I use this little piece of the board here? So the problem with, I don't want to get off in too much of a tangent, but first of all, do people understand Newton-Raphson? Does that make sense to you? Okay? You're not just making me feel good. If you have a question, ask it. Okay, so if you have, let's say you did this. You had some crazy function like this, right? Then well, you could have, like, I think this will screw it up. This thing would go here, right? And then you get this thing, and it would go here. And then this thing would go way out here, okay? And then it would come over here, and it would go way over here. You see what it's going to, it's not going to come out, it's not good, okay? So my point is, this is perfectly valid. It's a monotone increasing function, but it's going to cause big problems, right, for Newton-Raphson. So we're not going to do Newton-Raphson. However, there's a chapter coming up that's chalk, not coronavirus. It's called, I guess it's the next chapter. Chapter 8, called Surrogate Functions and Majorization. That could be retitled a modification of Newton-Raphson that works. So the surrogate functions and majorization is sort of a generalization of Newton-Raphson. It's not exactly a generalization. It's a modification of Newton-Raphson, which is widely used. It's a version of the distinction between surrogate functions and majorization and Newton-Raphson is that surrogate functions are guaranteed to converge. So you don't have this problem that the thing can be unstable, okay? And the problem is when you're working on big things, like if you're writing a big program on a piece of code and you put a few lines in there and you go, oh, it doesn't really matter. Like that parameter will never be 0. Like in that case, it'll just core dump, but it'll never happen. I don't have to worry about it. That is really horrible programming strategy, right? Because there's a rule in programming, which is that anything that can happen will happen. And that is actually very true. And the reason is everything in a piece of code happens 15 quadzillion times. So sooner or later, that crazy special case will occur, and your code will core dump. And if the F-16 pilot is at 30,000 feet when that happens, they're going to be very unhappy with you, okay? So you have to always make sure every special case gets handled, okay? So the thing is this, okay, now, so that's what surrogate functions are about. They're a version that always works, okay? Now, but right now we're not there yet. So instead, we're going to do something simpler. So instead, what we're going to do is this. We're going to say, okay, we have this function. It goes like that, okay? So how are we going to do it? We're going to start with 0, because we know the solution has to be somewhere 0. And we're going to have some other here value, and we'll say this is A equals 0, and then we'll say B equals something. We'll say some value that's guaranteed large enough that we know the solution, that the gradient has to be positive, and you can bound it in real cases. So then what you do is you say, okay, I'll take a halfway point in between, and I'll call this C. And I'll evaluate the function, the gradient at that point. And then I'll say, if the value of the gradient's positive, then I know that the solution had to fall somewhere between A and C. So call this function g of alpha, okay? So if g of c is greater than 0, then what I do is I set b equal to c. If g of c is less than 0, or say less than or equal, I set a equal to c. In other words, if this thing's above here, then I take this point and the solution has to fall in this interval. If, on the other hand, the curve kind of looked like this, okay, then I would say, this solution must fall in this side of the interval, right? Now you just keep repeating that until you get as many times as you want, basically. So let's say you do it n times. If you do it n times, then what ends up happening is you take b minus a, which was the original size of the interval, and you multiply it by 2 to the minus n, and that's what epsilon's going to be. Now, if you pick it to be 10, then it'll be like 2 to the 10th is about 1,000, 1024. So you'll do 1/10 of a percent. But that requires that you have 10 iterations. Each iteration requires, you don't have to compute theta 2, notice. That's the beauty. There's no theta 2, there's only theta 1. But you have to evaluate this theta 2 10 times, right? The formula is a little different, because now instead of computing it here, you put it at whatever the value of alpha is that you're using. Okay? Yeah. Okay, let me not write that because it's just going to read the notes, okay? But you have to compute the gradient 10 times, just at different points. And fine, so that's a lot of computation because that increases the complexity of your, the dominant computation for most of these algorithms for gradient descent is the line search, okay? So that means it's going to increase the complexity, the computational complexity of your algorithm by a factor of 10. Or not, it's going to increase the computation by about a factor of 10. So that's not good, because 10 is a pretty big number, okay? But let's say we do that. Then at the end, and I mentioned this last time, that when we're all finished, we have like a point here. So this is, so what'll happen is like, we'll have gotten it down where this is A and that's B, right? And we'll have it pretty close because we ran this a bunch of times. So this is 1/1000th, but it's magnified, okay? So then what we do is we go, oh, well, but we can draw a straight line between here and here and get an interpolated solution. That interpolated solution, as I mentioned earlier, is important because it gives you a continuous solution so that the optimization algorithm doesn't get stuck. So remember, my hope is that if you do this stuff, that when you hit these things, you won't actually remember what you have to do, but you'll just remember my voice and you'll remember, I remember you told me I had to do something. So you won't remember exactly what you have to do, but you'll just remember that you have to do something. And then you can go look it up and remember what you had to do, okay? You have to do this step right here. So I won't go through the details, but this basically computes exactly this point of intersection, given that you have a linear interpolation between the last two known points. So that's very important because it gives you a much more accurate, if it was a quadratic prior, this would give you the exact solution. So you'd only take one step, you'd be done. But with a non-quadratic prior, then it's not exact, but it's still a lot closer. Okay? Now, okay. The other thing is this, and this, okay, which is sort of important, that please read the notes, okay? Because the problem is I just can't go through all this detail, okay? But what happens is, if let's say you have, and we're assuming mostly in this class, that the forward model is always linear, okay? So the forward model, we can compute the first two derivatives of the forward model in a computationally efficient way, so So we have a functional quadratic form for the forward model. But the tricky part is the prior model. So the point here is this. When you go to compute these derivatives, you only have to do a forward model calculation once because you exploit its quadratic form. If it is quadratic, it's not always quadratic, but it's often quadratic. So you do the forward, you only have to compute the full gradient once. And then you can do this rooting like this. Okay, where you just, these are scalars. So you just computed theta 1 once, and you computed theta 2 once, and you just stored them, and you reuse them. So the 10 iterations you have to do don't actually require that you go back to the full forward model. Because the forward model is the thing that requires, say, convolution of the entire image. It's a computationally expensive part. Then you just need this prior model piece. The prior model piece is low computational because you just, it's a neighborhood operation where you just access the local pixels in the image. So in a lot of problems, this part of the computation, the forward model, is more computation than the prior. Not always, but often. In tomography, it's definitely the case. For the tomography, you have to do a projection through the image. Okay, so. Oh, shit, I did turn. There's a little needle going up and down. If it's not, I'm hosed. Okay, good. All right, thank goodness. Okay. If for some reason that should ever not be going up and down, please alert me. Okay, so then you have to compute these derivatives, and you're going to read the instructions. So you can compute this g function as a function of alpha in terms of those derivatives, of the derivatives of the potential. And remember, this potential function, when you differentiated this potential function, does anybody remember what the derivative of the potential function was? It had a name? It's the influence function. So you basically have to evaluate the influence function to compute these gradients. Okay? And then blah de blah de blah, and then that's it. Okay, so I think we're basically done this chapter, but you got to read it carefully. So the bottom line is this: I've swept everything under the rug, because all I did is I said, okay, we got this thing, we got to minimize it, and here's a brute force way of doing it using what's called half interval search. Okay, but half interval search is really not practical. So we don't really want to use it. In the lab, do you use half-interval search? I forget. I think you don't use half-interval search. There was an earlier version where you did. It'd be good to do it once just so you'd understand it. But so then you say, okay, so this is good, but it's not practical because it's way too slow. So that's what the next chapter is. The next chapter is surrogate functions, which is, what did I tell you this is? This is the practical version of Newton-Raphson. It's practical because it always works. So you don't have to worry about the code crashing while you're flying the F-16 in a loop. That would be bad. Can you imagine, like, you're coming around, maybe it's like really, it's a bad thing to end in, but that really happened. Oh no, it's not funny, okay? It involved a lot of very unhappiness. The Blue Angels, was it the Blue Angels or the Thunderbirds? I think it's the Blue Angels, were practicing, and the vertical stabilizer, the vertical flight surface, what do you call it, the elevator, on the lead plane broke. It didn't end well for all of them. So you don't want software failures in real-time systems. So you want this stuff to work correctly every time, okay? And that's why we're going to have these surrogate functions, and they're really cool. I'm going to just show you one last picture because I just love it so much, okay? Okay, I know I'm weird that a little diagram like this can be like so much fun, okay? Normal people don't feel that way, but I'm sorry. This is the way surrogate functions work. You have this function you're trying to minimize, it's nasty. So you take a simple function that's easy to deal with, usually quadratic, but not always, and you set it so it's just equal at the point you're at currently, and its tangent, but it upper bounds. And now you minimize the upper bounding function instead of the true function. Why? Because this function is easier to work with. Well, when you minimize the upper bounding function, you're guaranteed to have reduced the true function. And you're guaranteed that you didn't overshoot. So this is essentially a generalization of Newton-Raphson, which always works as long as you can find the upper bounding function. And this is what we're going to learn. It's called majorization. These are called surrogate functions. It's really cute, okay? All right, so I'll talk to you then next time on Wednesday, and thanks a lot. Bye.